Okay, my name is Shay and I'm from Cloudify. And I'm going to talk about edge computing. Actually, the cloud, as you see today, is going to broken to small autonomous actually clouds that are going to talk with each other. And I explained the use cases and why this is going to be in the future. Actually, I'm going to go over, explain what is edge computing, what's the problem statement, why we need it at all, why the current hybrid situations are not good enough to support this use case. I call it the return to the edge, and what are the orchestration models, and how we cope with all those challenges, the new challenges. So think about this. Actually, we work with several companies like this. Let's say you have here ships. Think that each ship actually needs to run many different services. It could be also planes or tracks and IoT in the future. Many devices that have many different sensors. Think about SpaceX from Elon Musk, that you send actually a spaceship up to the air and you need to work. There is no network connectivity there. How are you going to manage this? So there are many different challenges here. So if we look at the ship example, think about thousands of ships. A ship comes to shore for maintenance only once a year. If you want to apply the current CI/CD processes to the ship, you want to actually patch some security problems, you cannot do it online. So if we now focus on the problems, there is no network to those ships. So each ship needs to run a data center, a cloud actually, in this ship. Moreover, you have resource constraints. Today in those ships you actually have a rack and you have limited resources. So actually running VMs there takes a lot of resources. So we work with a company that they want to run their Docker with Kubernetes. Now moreover, you have some security issues. Let's say on those ships actually, you have many different applications actually coming in Docker from different VARs. Now users talk to different applications, so we need to apply and create service chains of firewalls, URL filtering, and moreover, one container actually can penetrate some other container. So what do we do with this? How do we apply all those security mechanisms? If we talk about bandwidth, now each ship actually is connected to the shore. If we go back here, each ship is connected to the shore through a satellite. Now, a satellite has a coverage, and this satellite is connected to a data center. So think about a service that is changed from the ship to the shore, and now the ship moves from one satellite coverage to another satellite coverage, which means it's connected now to a different data center. So if you were connected to a web content and a firewall, now you have to move those VMs, those VNFs with you to the next data center, or to put a pointer to the old VNFs. But you have lots of VNFs and lots of services, and you have a scalability issue here. You cannot just deploy VNFs as many as you want. You are actually need to track the service. So what do you do with this? Scale. I was talking about thousands of ships. Think about thousands of airplanes and many different IoT devices that I will touch later. Satellite coverage that I mentioned, that you lose satellite coverage when you move from one place to another place. And of course the service composition, how you define a service. Let's say a user on a mobile phone wants to use some internet, secure internet on the ship, or wants to go to some gambling applications, or want to even communicate with another user on the same ship. How do you know that this user can talk to the other user? How do you make those actually service definitions inside the ship itself? How do you make definitions of a service between a ship and a shore? And how you make this service definition between a ship, a shore, and a cloud that you know from today, a centralized cloud? So there are many different challenges that we need to cope with. And the problem of a ship actually is just one instance of the bigger problem. We are going to face a data tsunami ahead of us. Billions of connected devices, IoT devices, sensors are going to be connected now to the cloud. Think about connected cars, think about different IoT use cases. You don't have the time, latency, or to send so many data points back to the centralized cloud. You need to do all the decisions locally in real time and based on all these data points. So you need to apply machine learning methods, and you have to have many different ways to do everything locally. So we move now from a centralized cloud to local clouds. Think about, for example, at the last MWC, Mobile World Congress, many telcos actually presented different, they call it mobile edge computing. For example, Deutsche Telekom actually presented their race car, and I put augmented reality glasses on my face, and then I saw exactly everything that is coming from the course itself, from each car, and actually everything was actually from the car, from the course. They put different cameras, and was actually going to a computer in the booth, which acted as the mobile edge computing, and then to my face, which augmented or created all this overlay, which I saw the big picture. So think about two connected cars in your neighborhood that one can tell each other that you have a block in the road here, or hey, you have to stop because someone is coming from here. It cannot go to a centralized cloud because you don't have the latency time. By then you can have an accident. So many things now with the 5G and the IoT and the machine-to-machine is going to be changed. So we are going to face, by analysts say, by 2020, a huge tsunami of many sensors coming in, and we need to apply many different technologies to cope with it. So once, a few years ago, we thought that every person will have a computer, will have a mobile device. So think about it, it's something like billions, 10 billions of devices maximum. But now every person has lots of sensors around him. Even it's not just a person. Every machine now, everything talks to each other. So it's not just a person. We have something that you cannot understand. The scale here gets beyond any imagination. So there are not enough people actually today. Google, for example, it has 12 data centers. Each data center can be managed by 100 people. But if we talk about local clouds, how many people we need here? 1,000, 100,000, nothing that we can imagine. So everything should be zero touch provisioning, zero orchestration. I mean, no human touch. Actually, everything should be automated without any human touch. And we have many challenges. How do we do the management? How we do the security, the networking, capacity planning, scale, and of course, orchestration. So the current approach, the centralized approach actually that we have today, we have actually different clouds. The Google Cloud, the Amazon Cloud is not good enough. So it's like the mainframe in the old years. So we are now moving to a different paradigm. Even if we look at hybrid clouds that today we know to manage, for example, in Cloudify, we can run a service, Docker Swarm containers from AWS going to on-prem, Kubernetes on OpenStack, and to Google Cloud. We can chain those services. This is still centralized clouds, so you cannot actually cope with all the previous problems that I mentioned. So if we look at the paradigm, so at the far, let's say, the 1970, we had mainframes. Now we move to, you remember the PC? It was a PC connected to a mainframe. And then today everyone uses a mobile phone, connects to a service in the cloud. It's like the mainframe. So you have a big, big mainframe, everyone is connected to it. But that's not good enough. So we need to have intelligence at the edge. And what does it mean? It means that each local edge will have sensors. It will infer all the information from the data points. As machine learning will take local real-time decisions on this. So the move is driven by real-time decisions, by data, enormous data points. And we need intelligence on those local points, on local clouds. Many talk about this direction actually. It was starting with fog computing a few years ago, connecting to bridge between the edge and the cloud. Many talk about putting OpenStack at the edge, full OpenStack. Today there are implementations that you have controllers in the middle, in the centralized cloud, and just the compute at the edges. But Now everything moves to the edge. And we have a real challenge how we do this. So edge computing is a method of optimizing cloud computing systems by performing data processing and real-time decisions at the edge. So it's driven by real-time data. We have actually thousands of, it's not thousands, it's more than enormous number of data centers that needs to connect between themselves. So you can read about it. You can, it's mentioned like cloudlets, edge data centers. We all know the telco VCPE or UCPE that they want to change services at the edge and to have some security services change in the cloud. And we work with many like this. And some call it cloud in a box. So that's the new move to this kind of cloud. So in Cloudify, actually, Cloudify today can be a master orchestrator and a domain orchestrator. So Cloudify can actually go and provision resources and applications in a private cloud. It can talk to public clouds. It can create service chains between private and public, between public and public. For example, you run on Google Cloud data-driven analytics, and you run on Amazon on EC2 compute things, and you can chain them together. You can run development and testing, but I'm not going now to focus on this, but because this is the current situations and we have solution for that. I'm going to focus on the edge cloud, about delegation, autonomous execution at the edge itself. Okay, so here we actually can come up with multiple models. One model can be actually that a master orchestrator actually is connected to a cloud edge, and it can send tasks to be executed through a controller at the edge, actually the edge cloud, but still the master orchestrator decides what's going to be, and it's semi-autonomous because this actually edge doesn't live by itself. If it gets disconnected, it's not autonomous. The more interesting model is actually this model where everything is autonomous. You delegate actually the task to run here. So if we go back to a ship, think about containers running on bare metal, and all the applications, user is connected to different applications. You can apply different services across the chain, and this is running locally. Now, if it needs something from the shore, so it can actually extend the service and get some additional capabilities from the shore. But if the ship actually, ships, sometimes they are getting disconnected from because of satellites coverage for long hours from the shore, and they cannot communicate. And even when they communicate, the bandwidth is very poor. So this cloud runs autonomously. And actually, we in Cloudify developed some components to do this. So we have in Tosca, and I will touch this later, but we have in Tosca definitions how to compose a service that is built from small different microservices. We have a workflow engine, and we can actually delegate and execute those autonomous clouds. So basically, you can have Cloudify actually embedded here at the local cloud. So if we look at this Cloudify that is here, I'm talking about this point, so what are the characteristics of such a solution? It should be autonomous. If it gets disconnected, it still needs to be able to actually execute workloads, to service different kind of applications. It should be done, do self-healing. If something fails, it should bring up the VM, correct it, connect it correctly in the graph itself, and bring the service back to normal. It should be very modular, that I can change it on the fly. It should be API enabled. It should actually stitch itself into the fabric, SDN, OVS, whatever we have there. And it should be based on distributed architecture. Actually, in this model, if we go back here, actually, in this model, we still have hierarchy. So we have the autonomous cloud, but we can build hierarchy. And when we collect KPIs and we want to show you, we can show you a federated view. But if we take it even to the more extreme, we can have every cloud actually work on itself, and we can have symmetric clouds. And if we have time, I'll touch on it, but you don't need actually, each cloud can connect to each cloud symmetrically, so that's you know, the extreme case in this situation. So that's actually, we have the Cloudify as the master orchestrator, and we have Cloudify in a box or Cloudify at the edge to work autonomously on this box. Let's look at a real use case now from telcos and UCPE. So actually, the admin, you see the admin here, the penguin? So the admin wants to launch a new service. He talks to the master orchestrator here. And this master orchestrator actually sends something for execution to the local orchestrator. The local orchestrator instantiates the VM, bring the application, connect the service through different plugins, and now it sends back a notification that the service is up, and it also collects different KPIs about the infrastructure, about the service itself. So you can have a dashboard that displays different services running on local clouds. Basically, all those KPIs are, you know, they need to work in a scale. So you put them on a message bus, and then we have different mechanisms to collect the information and present the information. Any questions so far? And this is actually done automatically without any human intervention. All this process is running automatically, no human touch. Now, if something fails, it should auto-heal it. If something needs to scale, it should actually scale out or scale in where you don't need the resources anymore. Everything is autonomically here. Now, let's talk about how we do it. So till now, I explained why we need those local clouds, why we need to create all those new mechanisms, and let's see how Cloudify solves the situation here. So basically, in Cloudify, we have something that we call a blueprint. It's a Tosca blueprint that defines the topology. Tosca stands for Topology and Orchestration for Cloud Applications. So we actually input a service blueprint that we create to a blueprint parser that creates an execution plan, and then at the end, actually, after getting the right inputs, and we create a graph, a deployment graph. Let's think about this. This could be a VM or an application that is contained inside a VM, or a connection between one container and another container. Basically, if we look at this example, just to go quickly about what Tosca does, so you can see that here we have a VM, a group of resources that are connected to another Java application that runs inside a container or VM, and this Java application is actually connected to a database, to a MongoDB database here. The Java application is hosted on a container, but it's still, you see the Tomcat here, so it's running inside Tomcat inside a container. So in Tosca, you are able to express all those topologies and dependencies. So the Java application won't start to execute until the Mongo service is up and running and it is connected to it. And everything here is dynamic. So the ports are dynamic, the IP addresses are dynamic, everything is dynamic, and Cloudify knows to handle it. And based on the different inputs and outputs, actually, Cloudify can concatenate or compose together multiple microservices. So think about this example. You have multiple microservices, and we have a proxy pattern actually that knows to instantiate this microservice. This microservice has its own lifecycle events like init, configure, start, stop, and it can get inputs and sends out outputs back. Now, if we already have this microservice up and running, so it just consumes the outputs, it doesn't need to send inputs to instantiate it. Moreover, since we create the graph in memory, so we can traverse the graph in memory and add nodes to the graph, node instances, delete instances, so we can actually change the blueprint on the fly. In this example, we changed together a third microservice. So for example, in the case of UCPE or in a ship, let's say user from a ship connects through a firewall, and now I want to do URL filtering. There are kids on the ship. I don't want them to go to some certain websites. So I can add this functionality here. Basically, the whole model is very flexible, like the models of containers and serverless functions architectures. Now, if we actually take this, what I described here, the proxy pattern here, and we add requirements and capabilities, and let me explain what are requirements and capabilities. In Tosca, you can define, hey, I have interfaces, and I actually need, for example, I need a database, or I need a container from this and this type. And in the capabilities, when I launch a service, I say my service supports A, B, and C. Now, if you see a match between a requirement and a capability, so you can change them together. So in this case, you actually can create a Lego that connects different microservices together to obtain the whole service chain. So on the fly, you can create it. Now, today, we have a master blueprint that knows to create all this service ship to shore. But in the future, you can even use some discovery services. And like that, one service can ask, okay, who supports this? And the other service that supports those requirements say, I support it, and then you can connect them together. And you can create a very dynamic distributed service to support all this. So to summarize, actually, what we have, in the future, based on the different requirements, and we see it from current client customers and future IoT. By 2020, they say that we are going to have IoT all over. So you need to have local intelligence, local clouds actually operate autonomously. They will get all the different data from the sensors. They will infer based on machine learning or other AI algorithms what to do, and will take local decisions, and they will act upon it. The clouds, the centralized clouds that you know of today, I think will change their face, and actually they can connect multiple local data centers. They can do some other more end-to-end advanced algorithms, but the cloud is going to be broken to many, many different local clouds that are going to be connected between themselves. Okay, any questions? Okay, so let's think about what we can do with this. Actually, so think about a branch office here. You can run a whole network, many different services here, and like a VCP, UCPE. You can define firewalls. You can define different services here, and then connect it to the main cloud. Think about smart homes, smart cities, about all the water, the traffic lights, the connected cars, everything in a smart city. Point of presence, the same. All the energy industry, think about gas, electricity, everything. You have the smart meters, you have everything connected like IoT devices. Think about the military that needs its own isolation, its own ad hoc networks, etc. And mass transportation, actually. In airplanes, for example, you know how many sensors you have in an airplane? I was amazed. It's something like 200,000. They connect even a sensor to your seats. They want to know later on if you actually moved during the flight or not. So you have many sensors in the engine itself. So that's an airplane, one airplane. So think about how many sensors you have in a bus or you have in the traffic light, and you need to actually merge everything together in a local neighborhood or a local location. So that's huge, actually. So there are many use cases, and analysts claim that the world is going to change by 2020. So it's not so far from now, 2 years only. Okay, so thank you.